Let's consider another example. In this case, the function f of z is equal to 3 over 2 plus z. And we want to find the Taylor series in the case when z0 is equal to 0. That means the Maclaurin series. In this case, we also see that this function is in some sense equal to some geometric series, but we have the feeling of this, but how can we prove it? Well, we see that in the denominator we do not have 1 minus something, which we should have. So by dividing with 2 in the numerator and the denominator, we obtain this expression. So this 3 over 2 we can just take out of the fraction, and we obtain this expression. And in the denominator we can now, instead of having this plus sign, change it to some minus sign by doing this trick. 1 minus z over 2. So now we have something here which is the limit of a geometric series for the case when u is equal to minus z over 2. So we know that this is equal to the sum of u to the power of n, where u is just equal to minus z over 2. Well, we can continue. We can multiply this series by 3 over 2 like this. We can observe that this is just equal to minus 1/2 to the power of n times z to the power of n. So we obtain that the coefficients an is given by this expression. Now we know that the Maclaurin series is on this form. It should be n here, not 2, sorry. And in this case we know that this u was equal to minus z over 2, and the absolute value of u should be less than 1, so we must have this inequality satisfied. By multiplying with 2, we know that minus z is, the absolute value of minus z is just equal to the absolute value of z, and multiplying with 2 we obtain this inequality. So we know that this expression is valid for all z which satisfy this inequality, namely that the absolute value of z should be less than 2. So this is just a disk with center at z equal to 0 and with radius equal to 2. Let's also consider another example, the same example but where z0 is equal to 1 instead of 0. So in this case we want the following answer. We want the following series expression. z0 is now equal to 1, so the Taylor series should look generally like this. So let's keep this in mind. We want this expression for the term which we have to make in the power of n. So what we are having here is 3 over 2 plus z, and we have to make this into the sum of a geometric series. And what we need is some u which is of this form, z minus 1. So we want it z minus 1 here, And what are we doing then? Well, we just write set minus 1 and add 1. Then we obtain this denominator. Now we can add this 1 to 2 and we obtain in the denominator 3 plus set minus 1. So now we have something here which is what we like to call a u, but it's, well, we see that we do not have 1 here, which we should in the denominator of the limit for a geometric series. So why don't we just divide by 3 in the numerator and the denominator? Then we obtain 1 over 1 plus set minus 1 over 3. Well, now we are very close to have the limit of a geometric series, because we should have 1 over 1 minus u. We have 1 over 1 plus something. So we replace this plus by minus by doing the same trick as above. We replace the denominator by 1 minus minus 1 times this function. Then we obtain something which is the sum of a geometric series. So replacing this by u, we know that this expression must be equal to the sum of u to the power of n. And this is the u we are using. Minus 1 times set minus 1 over 3. And we know that this guy should have an absolute value less than 1. So this means that minus 1 times this should be less than 1, and the absolute value of minus something is just the same as the absolute value of where we ignore the minus sign. Then we obtain this inequality, and multiplying with 3 on both sides of the inequality, we obtain that the absolute value of set minus 1 should be less than 3. So this series, this series f of set equal to this sum is valid when we are in the disk with center at 1 and radius equal to 3. So we also see that this expression to the power of n can be replaced by minus 1 to the power of n over 3 to the power of n. So this is the an coefficients in the Taylor series in this case.